It is my pleasure to introduce our afternoon keynote speaker, Dr. Marzyeh Ghassemi, who is joining us remotely from Boston. Marzyeh has had and still have a distinguished career at the intersection of ML and health. She is a faculty member at Vector and assistant prof in MIT. She completed her PhD at MIT, where her research focused on machine learning in healthcare, exploring how to predict immediate and long-term patient needs to inform decisions in the intensive care unit and ambulatory care. Her current research interests include clinical risk prediction with semi-supervised learning and non-invasive patient phenotyping for behavioral conditions. Marzyeh is on the board of Women in Machine Learning and co-organized the NEREP's 2016 and 17 workshop on machine learning for health. Please join me in welcoming Dr. Marzyeh Ghassemi.
All right. Hi, everyone. I'm going to talk to you today about designing machine learning processes for equitable health systems. I'm going to take about a half hour, and then I think we have about 10 minutes for questions, but I'm sure the moderators will tell me if that's not correct. So the first thing that I'll open with is my group does healthy machine learning. We try to create actionable insights in human health. And we do this in 3 ways, and I'll cover research in these 3 areas. So the first thing that we might try to do is build machine learning models that work in healthcare data. And that requires its own set of technical challenges that you might want to overcome. The second set of things that we do is we try to audit healthcare systems using current state-of-the-art machine learning systems and see where there are gaps that may be addressed. And the final thing that we do, and this is maybe a more recent thing that I'll talk to you about at the end, is try to understand what sort of behaviors we really need to engender with machine learning models, because even the best model will be wrong sometimes. And we really want to make doctors better, not just show off that we have a fancy machine learning system. So let's pretend that we have a patient like Sumana who's having trouble breathing. I'm going to walk you very briefly through a paper that we wrote addressing this kind of a concern. So our clinical collaborators came to us with hospital data. It looks something like this. You have blood pressure, temperature, respiration rate, all of these different kinds of vitals that are happening over time. And then you want to do a game. You want to train a machine learning model to do real-time prediction. I'm using air quotes because it's not actual real time. This is not us in a hospital, predicting life or death every minute in real time. We are playing a patient's record forward in real time as if we are getting it in real time. And this is an important part of the game because machine learning models are being penalized for guessing wrong the thing you're trying to predict. And we tell them that the right answer is always what actually happened to the patient. So they need to guess that somebody would have gotten a drug at a specific time, that they would have died at a specific time, that they would have developed a condition at a specific time, right? So that's how we train these models. We often take a very large amount of data in these settings, right? So this is an earlier paper of mine, so it didn't even use that much data, right? So it used tens of thousands of ICU patients. We use different kinds of data. There are nice ways that machine learning models can integrate things like notes, vitals, and labs, even though they're different modalities, into a single matrix. If you have one matrix for a single patient, you concatenate several matrices for a whole hospital patients, and now you have a big tensor of data. You can throw this large tensor of data at recurrent or convolutional neural networks. And we found that by intelligently representing the data and also using state-of-the-art deep learning models, we were able to predict several interventions like invasive ventilation, non-invasive ventilation, a vasopressor, which is a kind of drug that ups your blood pressure, and then things like 2 different kinds of fluid boluses with better performance than others had in the past, and that was very cool. But we are certainly not the only people who do this kind of work. I would say, the fix is in, right? Clinical AI is here to stay. Clinical AI performs at or above humans across a range of tasks in the human lifespan. So each one of these lines that you see in this table, in a very nice paper Eric Topol wrote a little while ago, did what I did. They took a data set, they had some outcome, they trained a model, and then they reported a performance. But I want you to look at two things in this beautiful table, because we have doctors that are actually making these decisions. I want you to look at the N and the AUC. N is reported to be anywhere from a few hundred to several 100,000. And AUC is often reported as a single number. And so the question to you is, if you showed up to a hospital in Toronto and you were there for triage and they took a chest x-ray of you and they said, we really want to have you wait and see a doctor, but that's going to be 3 hours. We'd really like to instead, offer that you can have this machine learning model that's been trained on 700,000 chest x-rays to predict risk of pneumonia. And it does at or above state of the art, what a doctor would do for its performance. And it's going to tell you whether you're healthy or not, because if you're healthy, you can go home. You don't need to wait here in the emerge for the next 3 hours to see a doctor. You can just go home and you'll be fine. How many of you would take that? I always ask my students this, that it's completely bimodal distribution. Half of the students are like, give me the AI, I don't want to wait in the hospital. And the other half say, and the other half who are saying, maybe not, are saying that because yes, it was trained on 700,000 images. Yes, it does have a performance that is at or above whatever set of clinicians this was benchmarked against. But what if that data set didn't include a patient like me? Or what if that aggregate number actually hides poorer performance in a subgroup of patients like me? Because again, AI is learning from human practice. And so we know that embodied data could be a powerful force for good. But if we want AI to use this embodied data from human bodies to improve science and address medical harm, we need to have diverse data sets and think carefully about how we're using this data in a health setting. And health really lags right now as compared to other machine learning subfields when we think specifically about reproducibility. And so this is often because hospitals or healthcare systems think they're sitting on gold. They think that they can have their internal doctors mine that data forever, 1 paper per year. Our doctors look smart and great. And if they never share it with people, researchers in other settings, or if it's only shared based on this oligarchical, I know you, my name is on your paper network, then they control the use of this data. And so data is often not released to a research community in a health setting. Sometimes people cite privacy concerns. I'm actually very anti that concern for reasons you can ask me later in the Q&A. And so our field is really stymied in a way that general machine learning, computer vision, and natural language processing are not, because we're not able often to reproduce people's code, data, and leverage multiple data sets immediately after a paper is published, which is de rigueur in other places that we use machine learning. So let's think about that example I just talked about, right? Sumana goes into the hospital and they tell her, hey, 3 hours in the emerge, or we could give your chest x-ray to this model, state of the art, fancy paper, right now it'll say something about you. She might be wondering if this model will work for a patient like her. So let's try that out. Let's take the 3 largest chest x-ray data sets that are publicly available right now, that's over 700,000 images. Let's train a dense net, that's a kind of convolutional neural network, state of the art, to predict the no finding label. You are healthy, you don't have a condition. And then let's measure the false positive rate in different subpopulations. And we're going to call that the model underdiagnosis rate. Why are we going to call that underdiagnosis? Because if I falsely positively say that more women are healthy, then that would lead to a higher rate of women who are in this emerge situation getting sent home when actually they have a condition and they should stay and see the doctor. And so that's what we're going to compare. So we train this model, 700,000 images. We have an AUC on average that is better than any prior reported state-of-the-art model. So we would be in that table, right? Like if they reran this table of great models that do great things, like there would be a name, a number, and a check mark. We're doing well. But this model, the state-of-the-art model with over 700,000 images and the highest AUC on average that has been reported in the literature, has a larger underdiagnosis rate in female patients, young patients, Black patients, and patients on Medicaid insurance. And intersectional identities often have even heavier underdiagnosis rates than aggregated group. That means that if you are a Black or Hispanic female patient, then you are doing strictly worse than female patients in general or than white female patients. And you may say, you're making a very simple point. You're just saying that we should have some defined set of audits that needs to happen at some point, maybe across self-reported ethnicity, different insurance types, if those are available in your country, or different self-reported gender identity. But that can be really hard to do. So if we take some of the more complex models that are being trained now, because that's what does the best kind of prediction, right? Very simple models don't work that well. So if we take some of the complex contextual language models, so these are things like BERT, and we look specifically at SciBERT, and SciBERT is trained on academic articles. So it's trained on Common Crawl, right? So it goes out there, reads all the scientific articles, and then does text completion of a sentence where there are tokens missing based on the statistical patterns it's learned from scientific papers, okay? And so here we're gonna give it this prompt: blank race patient became belligerent and violent, sent to. This is a real sentence from a real note at a real hospital. And I just took out the patient's race, and I am asking the model to fill in that last part. So if I say that it is a Caucasian or white patient, the model fills in the blank with, they should be sent to the hospital. If I say that it is an African, African-American, or Black patient, then the model says they should be sent to prison. This is not a hypothetical concern, because lots of places use language models, clinical language models, scientific language models right now to do clinical note completion, to do chatbots, to do question answering. Famously, infamously, Babylon Health did this in the UK, and the NHS shut it down very quickly when it started discriminating against women for very common conditions. And these are not easily auditable. It's not simple to do one check and say, okay, we're fine. We did our one check. Everything is good here. Because the range of biases that you might experience are not easily addressed, even by technical solutions. So here, for example, somebody had asked me at some point, well, what if we use the data we have right now, which we know is biased and we know is imperfect? We build some models, and then later on, we collect much better data, right? That's our goal. We're going to collect much better data 5 years, right? Can we still use models that have been developed using that old biased data, right? So some embedding space, and then just rebalance the data and train a downstream classifier on top of this representation that we've learned. So we could learn a representation, a way of mapping examples to a ball, and then we throw that bad data away, but we save the ball because we have lots of data, we don't want to waste it. And we just train some sort of extra classifier that goes on top of that ball. So data gets mapped, balanced fair data gets mapped to the ball, and then I train a classifier that goes from these mapped examples to the outcome. It turns out the answer is no. When you balance data downstream, but then have the same biased embedding space in the middle, if you don't throw that away, all this intermediate bias that you learned is retained in your downstream task, even with perfectly rebalanced data. And that's because bias is really a strong part of all landscapes, but particularly in the clinical landscape. If there's a bias that you've seen in society, and these are sociology papers, right? This is just society has biases, humans have biases. You're going to see it in clinical care. And so the range of things you might need to audit for, check for, understand, they're not easily done in these sort of pro forma ways. So first pop quiz. You thought there were no quizzes, but I'm a professor, ha ha ha. So it's midterm season. This is a real nursing note from a real hospital. And I took out the patient's self-reported race from this note. Can you tell what this patient's race is? I hope the answer is no, because the doctors I tested in this published paper actually couldn't. So probably you can't either. If you can, call me. I want to know why. But machine learning models can. And in this case specifically, it makes sense why. It's because in the northeastern United States, specifically where we have a very small Black patient population, the Black patients tend to have a higher rate of hypertension, which is treated with dialysis. And so the model is not using maybe a social bias here. It's using a statistical bias, which we may say is valid, because it's true that this tends to be accurate in this proportion of the population. But it's not just accurate in a very small population or in, one hospital. We found that these models, even very simple models like logistic regression, up through more complex models like the Cybert model I mentioned, and then ensembles of this, are able to predict your self-reported race using cues from the clinical note after we redact the race in 2 large hospital data sets. Which is almost 60,000 patients and millions of notes. And it's not just using things that I think we would all say are reasonably fair game, like a higher comorbidity prevalence in a specific patient population. It's using things like, if you talk about skin at all, the patient is likely white. And that's because doctors in general, this is well documented in dermatology textbooks and also just in case studies, very, very few examples of this skin-related presentation of diseases are ever done in darker skin. Consequently, very few clinical staff members will note anything about the skin-related presentation of a disease in darker skin, which means there's a huge gap in diagnosing and treating people when they have these skin-related presentations of a disease and darker skin. We also found some things that were just personally different, like they seem like personal differences that are maybe potential biases that care staff have. So the word difficult, we found, is used a lot more to describe Black patients and their families. We checked to make sure that it wasn't difficult in a subjective way describing the condition. This is a difficult case of diabetes, or this patient is a difficult stick for a diabetic test. It's not that. They are describing the patients as more difficult. Patient families are also described differently. Even if you look at married female patients, where often a husband would be the person who is queried about care directives, if we're talking about ICU care or care where the patient is not able to make their own care directives. And we found that there's a significant difference in the way that families and next of kin and care directive authorizers are described. And these are just personal differences that are likely due to biases by the staff themselves. And so here the model is saying, on average, in aggregate, these little tiny differences, like, you never talk about darker skin. You think that darker skinned families are more difficult, all of these things. They may not make a difference on one individual person, but taken together, they are strong proxies for your identity. Here's your second pop quiz. This is harder because I just told you, and maybe you could have imagined this beforehand, that there are many proxies in clinical notes for your self-reported race. This is your own identification. It's not genetic ancestry. It's correlated with darker skin, but obviously there's a huge range of people who would identify as a Black Canadian or an African American, and it is not directly tied to genetic ancestry. Same thing with reporting white or Caucasian ethnicity in your EHR. And so here, it seems even worse, right? Like, how could a model tell if this patient is Black or not? There's no way, right? Because this is a self-reported ethnicity, right? It has nothing to do with your genetic ancestry. And all of those clues I just told you about, saying somebody's difficult, those are like another person being biased, right? And like writing something down a little bit different about you because you look a little bit different. But models can actually tell with even higher performance when somebody self-reports African-American race. And, because we were upset by this or shocked by this or didn't believe our students about this, not that that would be me, we tested a lot of hypotheses to figure out what is the proxy variable that the model is using here. So we told the radiologist we were working with, first we got data from several sites where we have a lot more African Americans. So from Emory Hospital, for example, where the population is 50-50. And then we asked radiologists, every single proxy that you think could be used here, tell us what it is, and we'll test it. And we did. It's not body mass index, it's not breast density, it's not bone density, and it's not the disease distribution, which was my hypothesis based on the note paper. In fact, you can bandpass filter these images until there's not really a lot of information in them that a clinician could use diagnostically. And the models are still pretty sure about somebody's self-reported race. I can tell you what I think this is. And of course, we can't 100% confirm this because we don't have photos of people's skin tone. We believe that this is the case because if you self-report African American or Black race, then your skin, we believe, is on average much darker than if you self-report white or Caucasian race. And so in the same way that it's been reported for many years now, and finally it's being addressed, commercial cameras are calibrated to only work well for lighter skinned subjects, right? So, when you click the camera, there's a lot of calibration about like the actual image that's captured and the range of tones that you can capture. And for the longest time, it just would not capture darker skin at all. And so there were actual fixes that were proposed where they said, like, the calibration that you do is always on this photograph of a light-skinned person. And that's causing all these cameras that go out to do very poorly in half of the population that they may be deployed in. And then, medical imaging devices are also calibrated, right? They're also calibrated at the beginning. And in the end, this is a radiation wave that is going out and interacting with somebody who has a different melanin level with maybe slightly different levels of spectrum blocking. And they're so insignificant that for us, we're like, what do you mean? Like, there's no difference. How could I detect that? But it's trivially obvious to a machine learning model that can detect these tiny aggregate differences in the noisy bounce back of these spectral signals that are going out and being recorded back. I'm going to talk really briefly about a common fix that is proposed to me that I don't believe in. So I'll disclose my bias ahead of time. Many people tell me, well, we can just fix these with explanations. Really, the problem here is that complex models can be hard to understand. So let's fix it with post-hoc explanations. This is a very common thing people propose, papers like Lime and Shop. Lime alone has over 8,000 citations. And so we took the most common local and global explanation methods that people use in the machine learning literature to explain a model post-hoc for trust, for fairness. And we decided to measure the fairness of these different methods. So when we train a black box, we have some performance. And then we're going to see what happens when we explain the model, see whether it makes our overall performance on different subgroups better or worse. And we're going to measure the difference between average fidelity and worst case fidelity, for example, between men and women, and then also the average absolute difference in fidelity across subgroups. And we're not just going to do this in a health setting, which is my usual thing. We will include data for that. We're also going to look at other data sets like the adult income data set, where we're looking at how much somebody might earn, and that's used by banks to determine likelihood of loan repayment. And we're going to look at two recidivism risk and legal bar exam passing data sets. And the recidivism risk example specifically is salient because companies already take this data, the data that we are using, use it to train models, and then slap an explanation method and then put it in front of a judge, and then judges use this to determine your bail. So we find that explaining a model induces subgroup fidelity gaps. That makes sense. A black box model is able to snake some boundary in some nonlinear way so that it gets as many people right as possible. But when you force it to reduce the dimension of the representation it uses, it makes more and more approximations. And we actually find that the gap varies with the dimension of the explanation you use. So the more you need to explain, the worse it gets. And this is because even, when you remove this group information, you can detect minority group from the representation that you've learned. And if you have to approximate somebody out, if you have to lose a little bit of performance somewhere, you're probably going to lose it on a rare or minority subset of your examples. So I will briefly go over two things that I'm excited about. The first is, instead of doing all of these weird fixes to models post-hoc, if you know that you need something that is explainable from the get-go, there are ways that machine learning can generate easy to use, easy to deploy, and easy to verify outputs like decision support checklists. The problem with the ones that we see in medicine right now is you have to get a panel of experts to come to a consensus in order to make them. And then years later, I love this paper, Hidden in Plain Sight, somebody will come along and audit that panel of experts consensus score that you made. You're all remembering what you think works. And they'll say, actually, that's biased and it over or under corrects risk for African Americans. So why don't we just train these things directly from the actual data that we have? And so that's what we did for a recent paper in December of last year. We created a mixed integer programming problem out of this and added problem-specific constraints. And here's an example. We took the data from an intensive care unit where they wanted us to predict who would die after CRRT, which is a aggressive end of life treatment. And if somebody's going to die right after you give it to them, you don't want to do it. But we also want to ensure fairness, right? Because just like with that chest x-ray example, I don't want to falsely, positively say all the female patients will die after you give them this, because then it would mean that more women would be denied this treatment when actually it would help them. So we built a first model checklist with no fairness constraints. But look at this beautiful checklist, guys. There's no gender being used here. There's no ethnicity being used. These are all legitimate medical, readings, right? And this is a wonderful checklist, said the doctors I work with, and they would deploy it. Predict mortality given CRRT if 3 or more of these are checked. But this checklist actually has a max false positive rate gap between white men and Black women of over 50% in test set. That's really bad. When you add in fairness constraints, which are a natural thing you can do in mixed integer programming, we reduce this down actually to something within our tolerance gap, but it's a trade-off, right? Like in all things in life, it's an optimization. If we don't get better data, there will be a trade-off between reducing gaps and overall performance. So the last thing I want to talk to you about is deployments. Hopefully I've convinced you that models will be wrong sometimes, even the good ones, and that when they're wrong, they're probably going to be wrong on minorities. So let's take a real example. There are crisis call lines. Every university has one, and usually there are non-university ones. And I volunteered for one. You get minimal training because you're making a decision that carries no liability. The person who is calling is going to get help no matter what. Either they're going to get medical services 90% of the time, or rarely you will need to send the police, and you only send the police if there's a risk of violence, okay? So we did an experiment where we gave a bunch of people, clinicians and non-clinicians, a call summary. We varied whether we said the person being called about was African-American or Muslim. And then we asked them to make a decision. Should they get medical help or police help? And importantly, we told them you only call for police help if there's a risk of violence. It's an if and only if. If there is a risk of violence, then you call the police, and you only call the police if there's a risk of violence, okay? And when we tested people at baseline, great news, everyone, they did not call the cops more on Black and Muslim people. That was a wonderful part of my day. It was great. And then we gave them some AI advice. We gave them some evil AI advice. We trained a GPT-2 model, it's very easy to do, to be really racist and always suggest that you should call the cops on Black and Muslim people. So we have a biased, evil GPT-2 model that will be giving advice to people. And then we have an unbiased, fair GPT-2 model that will be giving fair advice to people. And I thought in my naivety that this would be the big difference, that we would prove in our study that if you give bad advice to good people, you make them bad. And that would mean we need to, really focus on making good models, and good models are the thing to do, everyone. Like, that's very important. And then we had this 2 different ways of showing them the advice. We either gave them the flag. Remember, it's an if-then. We either told them our AI system has flagged this call for risk of violence, and if it was the racist one, it would always say that there was a flag for Black and Muslim people. Or we gave them the then. We said, you should call the police in this situation or call for medical help. And we made them do the same decision, right? So this I didn't think would matter at all. It turns out that, as I said, right, respondents are not more likely to call the police at baseline with no advice. When you give them biased, prescriptive advice, when you tell them what to do, clinicians and non-clinicians listen. They are much more likely to call the police. But when you give them the same evil AI advice, descriptively, you just say that there's a risk of violence, they are able to ignore it, and they retain their original fair decision-making, which is nuts, I have to tell you, like completely unexpected research result. And this is really to say, in closing, there's no simple fixes for ethical AI in health. If we want to move forward in this space, we need to consider this entire pipeline and think about the sources of bias in the data that we have for problem selection and data collection, evaluate our models comprehensively when we define our outcomes and do algorithm and development, and then understand in post-deployment considerations that not all gaps can be corrected. And so we need to mitigate how they will be absorbed, potentially by deploying them with different caveats. And, I also want to say, if somebody tells you there's a simple fix, they're probably wrong. If they say, just explain it and everything will be fine, understand that really there is no way to just shortcut some of these issues. We need to work towards data, model, and processes that are reproducible, transparent, and fair. This is work that's been done by a fantastic group of students who have all really wowed me in their progress in this space in the last year or so. And I hope I've convinced you that we can learn robust models, audit diverse data, and deploy fair advice to create actionable insights in human health.
Thank you so much, Marzyeh, for your excellent and very insightful presentation. I'm sure many of us benefited from your insight and perspective. So we have time for a few questions from the audience in the room. Shams, go ahead.
Thank you for the great, really, really cool talk. I'm wondering, I guess, if you were the person to make the decision to deploy or not deploy a model, what decision boundary would you use and what tests would you do to decide, I guess, if it's like fair enough or has enough utility in the world?
Somebody's knocking on my door. I have to leave right now. I think that
I'm knocking.
It depends on actually the situation, right? So like, I would say there are some things like that I think are these perfect cases. So I'll give you two examples that they're things I really think we should be deploying right now, like right now. There are things like gynecological cancer screening, where on average it takes 10 years or more, depending on the cancer type, for your clinician to detect that you have it. And at that point, you have like stage 4, you're done, right? And so in those settings where, screening doesn't carry a huge burden and detection is already so bad, I feel like, the risk is so low. And so actually my threshold would be pretty low in that.
Oh, we lost you, Marzyeh.
That case for deploying a model, really it would. We're bad as a health system at detecting these things. And we know that any additional screening, the risk of it is relatively low, especially as compared to the outcome, which is often death. So in those cases, I would have a reasonably low threshold. The problem is in many of the cases where the light is shining, we have the data, those are acute care situations where there is a lot of data. Doctors are there, they are watching you, the instruments are going, there's a lot of information. It's a little bit harder to figure out what an appropriate threshold is in that case, just because like there are real risks to many of these treatments in acute care settings, right? Do you give somebody more vasopressors? Maybe. That's not actually great for your body either, right? And so I think it does need to depend on exactly like the kind of situation you're in.
Great, thank you. Yeah, one more question. Okay, go ahead. Go ahead.
Thanks so much for your talk. That was really interesting, and there's lots of large challenges, I think, to think about. I just had a question that's very maybe theoretical about, I guess I'm just wondering if there's been any conversations or thoughts about tackling this in reverse and using AI to try and retrain clinicians about their biases, to see if there's some kind of re-education that could be done, because so much bias exists in notes, for example, without people maybe realizing that that's a thing.
So are you a clinician?
I'm not.
I imagined not, no, like for suggesting this actually. So here's the problem. I often speak about the dangers of naively training and deploying AI, okay? It's a big thing that I care about a lot. And then I'll have somebody come up to me and say, I knew the AI was going to kill us. And I'll say the robots aren't coming for you like of their own volition. They're coming for you because they're learning from the doctors that certain groups tend to get undertreated, overtreated, mistreated, right? So the real problem here is the human system that is generating the data is not good labeled data. We don't want to reproduce that in a machine because that'll perpetuate care that we don't want perpetuated, that we would like to improve. And so I would be a huge proponent of using some of these systems to assist doctors in understanding that maybe there are certain gaps in their care, or they have certain missed opportunities to provide care to patients. And I think there's been a lot of very good research, not machine learning research, just good, epidemiological research to say that when you try interventions, for example, it's well known that male physicians specifically and exclusively miss heart attack in female patients that present in the hospital with these symptoms. It doesn't happen for female physicians to either gender patient, and it doesn't happen for female patients and female physicians. It's just this combination. But if you have the doctor train with more female colleagues, or they see more female patients, then they do better. And so clearly there are things you can do. I think the issue is, with everything else that's happening within many healthcare systems, often it's just one extra thing. And so I'm a huge fan of this. And I would be very happy if healthcare systems bought in and thought that this was an interesting thing. Just like we make pilots do a certain amount of hours in simulation to recertify on some regular basis as a regulatory agency, right? The FAA does that here. You could imagine doing something like that, but it all has to be accounted for somewhere. And it's not like clinical staff are relaxing on an island, thinking about all these extra things they could do with their massive amounts of spare time.
Great. So we are right on time. Thank you so much, Marzyeh. We are grateful for the time and effort you took to share your thoughts with us toward responsible AI and in particular health equity. Thank you.